In this part, we'll look at thermodynamic steam traps. A thermodynamic trap contains a component, such as a disc or a piston, that responds to variations in velocity and pressure that are related to changes in state of the incoming fluid. We'll look at a typical disc-type thermodynamic trap. This example is a tilting disc trap. It's designed to handle low to medium condensate flow. As its name suggests, the trap contains a disc that lifts or tilts. The disc is the trap's only moving part. At startup, the disc rests on seating surfaces that contact the trap's inlet and outlet. With the disc in this position, the trap is closed. When relatively cool condensate enters the trap, the flow lifts the disc up and opens the trap. The condensate then flows through the outlet and is discharged. During normal operation, hot condensate entering the trap experiences an increase in velocity and a reduction in pressure. As a result, some of the liquid condensate changes state, flashing to steam. Because steam has a greater volume than an equivalent weight of condensate, the velocity of the flow through the trap greatly increases after the flash steam has been generated. This further increase in velocity reduces pressure on the underside of the disc. At the same time, flashing condensate flows out and causes a pressure buildup in the area above the disc. When sufficient pressure builds up here, while pressure on the underside of the disc has been reduced, the disc is forced down onto the seating surfaces, which closes the trap. The disc is held closed by the pressure of the steam that's in the chamber above the disc. When this steam condenses, changing to a liquid state, and the pressure above the disc becomes low enough, the disc rises and condensate flows out, until velocity and pressure conditions within the trap again cause the disc to snap down on the seating surfaces, closing the trap. If the temperature and pressure at the trap inlet remain constant, a disc trap opens and closes at regular intervals. That is, the trap operates on a time cycle. Because it operates on a time cycle, as long as the temperature and pressure at the trap inlet remain constant, a disc trap stays closed for the same amount of time, typically 5 to 10 seconds, each time that it closes. Condensate that comes to the trap in the middle of a time cycle won't be discharged until the pressure above the disc falls low enough to allow the disc to rise and reopen the trap. Since the movement of the disc cycles between the open and the shut positions, the discharge from the trap is intermittent. Many of the maintenance problems associated with thermodynamic steam traps are due to wear of the trap components. Thermodynamic traps are very sensitive to scale or dirt that gets lodged on the seating surfaces. For this reason, a strainer should always be installed at the trap inlet. The strainer should be cleaned or blown down frequently to be sure that it remains free of debris and does not become clogged. Thermodynamic traps that are exposed to adverse weather conditions, such as rain, may begin to cycle more frequently than normal. When this happens, the moving parts of the trap wear out faster simply because they operate more frequently. Manufacturers provide various solutions to this problem. Some manufacturers make thermodynamic traps with double-walled bodies. Steam or condensate that enters a double-walled trap first flows around the outside of the internal parts and then into the trap. The warm condensate or steam keeps the internal parts at a relatively even temperature. Another way to protect a trap from adverse weather conditions is to use a bonnet cover. The bonnet is the top of the trap casing, and a bonnet cover is a metal cap that's placed over the top of the trap. The airspace between the cap and the trap body acts as an insulator and protects the trap from the weather.